Good afternoon. My name is Peter Rizun, and today I'm going to be speaking about my paper, A Transaction Fee Market Exists Without a Block Size Limit. I have that asterisk there to remind me that there's two provisos to this claim. Number one, we need for Bitcoin's inflation rate to be non-zero. And number two, we need for more than one miner or mining pool to exist. Now, underneath my blazer, I'm wearing my Bitcoin Miners t-shirt. This helps me to think like a Bitcoin miner. Now, most people think that the job of a miner is to find the magic nonce value that allows a new block to be appended to the blockchain. While that is true, miners have another job as well. Miners are also commodity producers. They produce a new type of digital commodity, unlike anything the world has ever seen before, called block space, or room in a block for transactional data. Now, before I explain why block space can be considered a normal economic commodity, let's first explore what the field of economics tells us about the production of such commodities. In this talk, we'll be looking at several charts, and they'll all share the same axes. On the horizontal, we'll plot the quantity of the commodity. That's the total number of apples produced per year, or the total number of bytes per block. On the vertical, we'll plot the unit price of the commodity. That's the price of one apple, or the price of one transaction's worth of block space. The coordinates of a point thus simultaneously represent the price and quantity of that commodity. The law of demand states that as the unit price for a commodity increases, the total quantity demanded by the market tends to decrease. Conversely, as the price falls, the total quantity increases. Now we can imagine appending a bunch of points like that to form what's called the demand curve. Now what's interesting about the demand curve is that if the price per unit gets low enough, the quantity demanded can become arbitrarily high. In other words, demand can be considered infinite. Now this is something I hear regarding the block size limit debate. People say, we need a limit because the demand for block space can be considered infinite. Well, economists struggled with that conundrum too, but they solved it over 100 years ago now. And the way they wrapped their head around it was to postulate a new law that, as you might have guessed, is called the law of supply. The law of supply is sort of the opposite to the law of demand. It says that producers will only produce more if they get paid more to do so. Apple farmers will only plant more trees if they can make more money by doing so. Bitcoin miners will only make their blocks bigger if they get more Bitcoins for doing so. The supply curve thus has a positive slope, the demand curve has a negative slope, and the two intersect here at what's called the free market equilibrium. The point on the vertical is the P star, and the point on the horizontal is Q star, the equilibrium quantity produced. Again, even though demand can be considered infinite, we still get a finite quantity produced. So is block space a normal economic commodity? Well, does it satisfy the laws of supply and demand? I think everybody here agrees that it satisfies the law of demand. It just makes sense that as the unit price for writing to the blockchain decreases, more data will get written to the blockchain. But does block space also satisfy the law of supply? At first glance, it might seem that a miner could just add as many transactions to he wants for free to a block. If that were the case, then the supply curve would flatline at zero like this. Supply and demand would never meet, and we'd have a tragedy of the commons where our blockchain fills up with spam. Now, to solve this problem, I use the scare quotes because it's not really a problem, as we'll see later, but there was a recent proposal called FlexCap. And FlexCap is interesting because it basically is artificially simulating the supply curve of a normal commodity. The idea is that the network would charge miners more and more the bigger they wanted to make their blocks. This would result in a forced equilibrium as opposed to a free market equilibrium, but a finite quantity of block space nonetheless. Now there's one big problem with FlexCap. It's that it requires a centralized group of people to decide what is the right price for block space. And if a centralized group of people get to decide that, well, then they can also decide winners and losers by adjusting that price. Fortunately, we don't need cap due to a phenomenon called orphaning that I'll describe next. So what is orphaning? Well, normally when a miner finds a block, he turns purple here, he broadcasts it to the other miners. They all start happily mining away, and if that guy at the bottom there finds a block a little bit later, well, everybody ignores him. The miner at the top is happy he gets the block reward. Now let's imagine that this time that miner mines a really big block. It propagates more slowly. Now when our miner at the bottom mines his small block, his spreads much faster. Everybody thinks the small block came first, even though it didn't. The miner at the top loses the block reward. His block gets orphaned. But the miner at the bottom, he's happy. Now, orphaning isn't some hypothetical theoretical construct. It really happens. There were 155 blocks orphaned in the first quarter of this year, and 97 orphaned in the second quarter, for about a 1% orphaning rate. So now that we know that orphaning is real, how does it affect the miner's cost of production for block space? Well, if a miner finds a block, he gets the block reward plus any fees from the transactions included in his block. If we want to look at his expected revenue per block, well, that's what he would earn multiplied by his probability of winning that block, which is just the ratio of his hash rate to the network hash rate. Now this is almost exact, but we need one more term to account for the fact that the bigger the block is, the more likely it is to be orphaned. My paper shows that we can model this as a decaying exponential in the propagation time. Now there's two things the miner here can control. He can control the fees, and he can control the propagation time. He can get more fees by making his block bigger, but he can have a less chance of orphaning by making his block smaller. In other words, the miner must choose to balance between fees and orphaning risk in order to maximize profit. Okay, so anyways, with a bit of algebra and a bit of calculus, it follows from that equation that the cost per byte for the miner to produce block space is proportional to Bitcoin's inflation rate times a term that grows exponentially in the propagation time. This is exciting because we're showing that there's a real cost to produce block space. But it also brings up proviso number 1 from the beginning. If the inflation rate is 0 when the block reward runs out, it's not clear what happens to the production costs. Anyways, what we want to do is we want to get a supply curve. So we want to get that equation in terms of the total quantity of the commodity produced. There's a theorem from physics called the Shannon-Hartley theorem, which basically says that the amount of time it takes to communicate some amount of information is proportional to the amount of information communicated. We can use that to write the cost per byte instead of as to the propagation time to something called the propagation impedance times the block size. The propagation impedance is just how many seconds it takes to communicate a megabyte of block information. So this is pretty cool because now we've shown that the cost grows exponentially in the block size. Why is that cool? Because, well, let's go back to our supply curve. Remember, FlexCap wanted to make that supply curve increase so it got more expensive the bigger the block gets. Well, we've shown that Bitcoin already has that property. It already behaves exactly like this. But instead of a forced market equilibrium, we would get a free market equilibrium. If we get a bunch more users coming in and demand for block space increases, well, that shifts the demand curve up. The price for block space goes up, the quantity produced gets a bit bigger, but we still reach an equilibrium point. If later miners work together and they can more efficiently propagate their blocks, well, that drops the supply curve. The price falls, the total quantity grows, but we still achieve equilibrium. In other words, a free market exists without a block size limit. Objections. What if a group of miners decides everyone's block contents beforehand? So the idea is that they all decide what they're working on beforehand. So this group of miners, they never orphan each other's blocks. Well, sure, that's called a mining pool. But that doesn't affect the fee market because the mining pools still need to transmit the block solutions between each other. Last proviso, I said we needed the inflation rate to be non-zero, and I said we needed more than one miner or mining pool to exist. If everybody joins the same pool, well, now there's nobody to lose orphan races to, and the fee market no longer holds. Okay, so I've explained that we don't strictly need a block size limit, but do we want a block size limit? Well, economics helps us to answer that question too. When Satoshi Nakamoto first put the block size limit in place, it served as an anti-spam measure. It was above the free market equilibrium point, so it didn't distort the free market dynamics. It was actually 800 times greater than Q star, so it would have been like a block down the road that way instead. Over the last 5 years, Bitcoin has grown tremendously, and I now believe the block size limit is on this side of Q star. It's now acting as a political measure, and is resulting in what economics calls a dead weight loss. That's the loss of economic activity as a result of this production quota. Now, some people think that production quotas can still be positive if they serve to reduce or eliminate some negative externality. I'm not going to weigh in on whether I think a negative externality exists. Instead, I'm going to say, how could a group enforce a production quota against the will of the market? The market wants to be at Q star, the production quota is forcing it to be at Q max. How will a group fight the invisible hand of the market? Well, I think they would follow the playbook of other command and control regimes. They would probably censor people who speak out against the quota to make it seem like everybody thinks the quota is a good idea. So this is not a completely hypothetical example. Then we have our obligatory Star Wars misquote. And indeed, we see that nodes are slipping through their fingers. Lastly, we'd expect attacks on infrastructure. And indeed, that is exactly what we're seeing. In the end, I believe the production quota would fail. And the reason is because we can only really enforce the rules that most people agree with anyways. Bitcoin will break down dams erected by special interest groups attempting to block the stream of transactions. That's all I have to say on the transaction fee market. Before I go, I wanted to follow up with what Andrew Miller said. So we are very excited to be launching Ledger, the world's first peer-reviewed academic journal dedicated to Bitcoin research. We are proud to be supported by a distinguished editorial board with leaders from academia and Bitcoin industry. We have Oxford, Cornell, Stanford, Coin Center, Blockstream, Ethereum, New York Law School, MIT, Duke University, all represented. And we will be making our call for papers on Tuesday. So listen up, guys. Thank you.
Woo! Peter.